thanks everybody for coming out. I'm always pleased to be able to talk about this with people who are interested. The whole notion of buildings as a potentially really meaningful response to climate change and action to kind of start to slow it down and as you'll see, also play a role in reversing it is really what is motivating me these days, and so I'm glad to see some people who share that. So I give this presentation a lot to people who have spent the majority of their careers in energy efficient building, because that tends to be the folks who took an interest in climate change fairly early on. A lot of people who are passionate about energy efficient buildings as a sort of understandable response to climate change. If we can have buildings that emit less, then that would be an impact on climate change. But I've been doing quite a bit of research as well as hands-on building these days, and sort of looking to see where energy efficiency is meaningful and where material selection might be more useful. So I'm not going to spend any time browbeating you about climate change. Presumably, if you're in this room, you have some sense that it's real and some sense that we should probably be doing something about it fairly soon. But the thing that has really been motivating me, and I do come from a practice where energy efficiency as a climate change response has been a big part of my work, is sort of the realization that we can't just reduce the emissions from buildings and hope to have the kind of impact that we need to have on climate change. And this little graph here, which is from Architecture 2030, what it shows is that although the sort of emissions from buildings, from operating buildings, here I'm using the number 28%. You can read various numbers anywhere from sort of 25 to 40% of planetary emissions come from the operation of buildings. But the sort of the part of that that's not often looked at is the emissions that come from making the materials to make buildings in the first place. So if we want to have true zero emission buildings, we have to not only look at the operational side, but we need to look at the embodied carbon side. And the biggest reason for that on this graph, this is just generic numbers from Architecture 2030, but that big yellow band at the bottom of that graph is the amount of emissions that come from harvesting and manufacturing building materials and not from the operations of the building. And so if you think about those emissions, the day that somebody sticks the key in the door of the new building, all of those material related emissions have already happened. So on day one of that building, that yellow bar is all there because all of those emissions have happened, all of those materials have been harvested and transported and manufactured and installed. So a building starts off sort of with like a big bang of carbon emissions, and then the blue slope on that graph is each year some operational emissions are associated with that building, which obviously grow over time. So you can see if you take that bar all the way out to 100 years from now, the operational side and the embodied emissions from the materials start to be of about the same weight. But if you look where I've got the little dotted line, which is around 2030, which is when all the climate scientists are telling us we need to start getting our emissions pretty close to zero, or at least cutting them in half. By that window, almost all of the emissions that a building is responsible for are from the materials, and only a very small portion are from the operations. So it's not to discount operational emissions by any means. They are significant, and with all the existing buildings we have emitting annually, that's a big problem too. But on the new building side, the embodied carbon emissions, those ones that come from the materials, are the sort of biggest piece of the pie that we have to deal with in the sort of short window of time that we have to deal with climate change. So, yeah, basically showing that small blue section is, we can make all the net zero buildings we want. All we'll be doing is making that blue line lower, but we won't have addressed that big yellow bar at the bottom. So the term embodied carbon is what the sort of academic community and the building world has sort of picked as a term for the emissions that are due to materials being harvested and manufactured. I think it's a terrible term because it makes it sound like we're talking about carbon that's in the materials, which we're not. But the term embodied carbon is, basically adding up. If say I'm going to pour some concrete, adding up the emissions of taking that limestone out of the ground, the equipment that was used to do that, transporting it to a cement factory, the fuel that goes into those kilns, the CO2 that comes out of the rocks as you're heating them up, basically all of those emissions the whole way along in order to create a material. And so you can see that, again, this is from Architecture 2030, their numbers, but between now and 2050, they're sort of seeing that about half of all building-related emissions will be from making materials, and the other half will be from operating buildings. So if we're going to address the whole notion of, well, we need to start building with materials that are responsible for smaller quantities of those emissions, we need to know what are the numbers that are associated with various materials, and how do we know what's a good choice and a less than good choice when we're looking at materials. And mostly these numbers come from reports called environmental product declarations, or EPDs, and that's a sort of third-party document. So a material manufacturer hires a third party to look at their entire production facility and come up not just with embodied carbon figures, but also a whole host of environmental impacts. So you can see there's global warming potential is what we're looking at for embodied carbon, but they also have acidification, eutrophication, ozone depletion, smog, resource use across the entire spectrum of making that product. But we're basically taking that GWP, that global warming potential figure, and that is given for a particular unit of a product. And so then if I'm designing a building, I can say, well, I'm using X number of kilograms of that product, or X number of square feet of it, or cubic feet, however the global warming potential has been expressed. And I can sort of multiply that out by the amount of that material I'm going to use, and get a sense of what the carbon footprint of those materials will be. So I had been working with these numbers for a while. I came across this notion of embodied carbon in 2012 or 2013. A British group at the University of Bath released a publicly accessible database of the embodied carbon of a whole really wide range of building materials. It's called the ICE database, the Inventory of Carbon and Energy. And at the time, I was writing a book called Making Better Buildings, where I was trying to sort of give readers a bunch of definable categories for sustainable building materials. And when I started the book, embodied carbon wasn't really on my radar. I don't think it was on very many people's radar at that point, but I stumbled into this database, and I thought, well, here's all these figures, I'll attach them to the materials I'm looking at. It was a fairly easy thing to do. And then as I started to do that, it dawned on me that some of these numbers were really, really, really big, and kind of alarmingly large, and some were really surprisingly small. And so I started doing this type of carbon footprint analysis for the buildings that I was doing in my own practice, and getting some really interesting numbers. And in fact, most of my buildings were getting negative numbers, which I'll get into in a second. But that made me think, well, I'm just doing this like a citizen scientist. I should really go to school and learn how to do this properly. So 3 years ago, I started a master's degree at Trent University to specifically look at embodied carbon in buildings. And so that all the results I'm going to show you today are from that study. And so what I was looking at was 2 different buildings. So the 2 that are on the screen there, one is just a small 1,000 square footprint raised bungalow, and then that 4-story, 8-unit multi-unit building. So definitely looking at sort of low-rise buildings, definitely looking at the residential sector. And what I wanted to do was model basically all the materials that I could find data for that you could feasibly use to build these buildings. And then I wanted to look at them at 2 different levels of energy efficiency. So I took the same 2 buildings and I had them meet sort of our code minimum standards in Ontario, Canada. And then I also did them as though they were being built to meet the net zero ready energy codes that are coming in Canada in 2030. So basically, what happens if you just build it at the minimums right now? What happens if you improve the energy efficiency? And I wanted to see, were there trade-offs? Were we actually causing more emissions by adding more insulation to a building than it was going to save in operating? And then I also created energy models for those buildings. So I did have some accurate sense of what the operational emissions would be for both those buildings in both of those forms of energy efficiency. And then I sort of put all the numbers together to see how the embodied and the operational emissions compared to each other. So for the data nerds in the room, these are the R value factors and some of the assumptions for both the energy efficient and the code compliant one. Our energy codes in Ontario are actually pretty good right now. When I started the study, I was working with the previous version of our code, and the numbers were a lot different. But now in our area, like R60 is the minimum in a roof, which is pretty hefty for most places, and walls in the sort of R24 range, and it's a pretty good code minimum. The results looked more interesting in this study when I was using the older code, but they're still quite. There's a lot of interesting stuff comes out of them. So the floor area for the buildings was always kept constant. So if I was adding more insulation to the building, I was adding it to the exterior so that everything else for the building stayed constant. So then I found EPDs for about 340 different building materials that you would feasibly use for buildings of that scale. So everything that I was modeling had to be something that somebody had already made a code-approved building out of. So even the more alternative materials, like everything is something that has already had precedent as being built in our climate to these code levels. And so I hunted down as many of these environmental product declarations as I could, and I kind of ranked them in the order that you see here. So sometimes the EPDs are done by an entire industry. So for example, the wood industry, everybody in the entire wood industry in North America collaborated on one EPD. So there's one set of figures, and it covers like all the member mills in North America. So some of them might have a lot lower carbon footprint, some of them might have a lot higher, but it's an average. And if there were no industry average EPDs, then I would gather as many ones that had been done by specific manufacturers as I could find, and I averaged those. And if I couldn't find any North American data, then I would switch to European data and looking for industry average ones or averaging out a bunch of product specific ones. So then, don't worry too much about soaking up all of the numbers from this, but this is sort of what what that initial embodied carbon analysis looked like. So everything on the left were sort of on the higher end of the spectrum of carbon footprint. So those were all the options I looked at that ended up having a pretty high carbon footprint. And on the right are the ones that are slightly lower. And so the ones that I pulled out in bold are sort of the best examples of both of those. So for example, for the slab floor with R15 of insulation underneath it, the biggest emitter was a typical concrete slab with XPS foam under it. And that was responsible for 25 tons of emissions for this one 8-unit building. So that's when when I first started looking at these numbers, that's when my jaw started hitting the floor. Like when one small building, one aspect, like one element of one small building is responsible for 25 tons. You start to do the multiplication of how many of these things we build. It starts to be pretty large, and you can see as you sort of go down that list that if we do typical concrete with HFC spray foam, it's 12 tons. The same slab with foam glass insulation is also 12 tons, and there's a few that get you down into sort of the 10-ton range. Over on the other side, the best slab floor I looked at was an adobe floor, so an earth-based floor with expanded glass aggregate. It's a product called Glavel that's a puffed up recycled glass. And so that slab and insulation was only responsible for 1 ton of emissions. So you got some 25-ton and 12 and 10-ton examples on the high side, and some 1.5 ton examples on the other side. So right away it's like, oh, material choices really matter. We can make a pretty big difference just by thinking about the materials we spec and knowing what their carbon footprint is. And so then on the bottom left, the foundation, again, the highest emitter was an 8-inch concrete wall with XPS foam on it, and that was 14 tons. And you can see, again, there's a range on the high side between sort of like 9 and 4 tons. But then over on the better material choices side, the number that's in green is a negative number. That's negative 2.6 tons or 2,600 kilograms. And there's also a hempcrete example underneath that's minus 505 kilograms or half a ton. So that gets head scratching. It's like, well, what is a negative emission? How can you have a material that is responsible for negative emissions? And what those are, they're plant-based materials. And the reason they can have negative emissions associated with them is those plants have actually absorbed CO2 to build themselves. So that carbon was in the atmosphere very recently. They've pulled it out, separated the C and the O, and used the C to build their own cellular structure. And so materials with negative emissions, if you have a plant-based material, there are still emissions associated with like growing it and harvesting it and transporting it. But in general, most of those plant-based materials, the carbon that's stored in the material outweighs the carbon that was emitted in the production thing. And so we end up with a whole range of materials that actually have this sort of carbon capture and storage potential that actually become negative numbers in this kind of accounting, and it's a bit of a game changer. So I like to look at the pictures of all the machines that humans are inventing right now, like this thing here, that we're designing to pull CO2 out of the atmosphere and turn into useful products. But then all around us, all over the world, there are plants. That's what they do. They are the best CO2 extraction machines that have ever been invented. They draw down billions of tons a year. And so what we haven't been very good at as humans, but in particular as builders, is taking advantage of that, of seeing like what can we actually do with these plant-based materials, how much of them can we feasibly incorporate into a building. So now as we go through some of the other sort of main categories of products and emissions, you'll start to see a whole bunch of those negative numbers showing up, and the negative numbers are all associated with plant-based materials. So it might be the cedar or the pine cladding. The clay plaster has a lot of chopped straw on it, so that's where its negative carbon content is coming from. Down there on the right for the exterior walls, a wood frame with straw insulation and wood fiberboard sheathing has a pretty high negative number, but so does a number of other things, including hempcrete, fiberboard, cellulose insulation, CLT, which is cross-laminated timber. There are all kinds of sort of pretty feasible building materials that we can use that have negative emissions, and that's in pretty stark contrast to some of the ones over on the left there, where your sort of typical cement brick on that building would have 21 tons of emissions associated with it, versus having sort of negative 8 tons if we clad that in cedar or pine. And again, you can see on the exterior walls, buildings of this scale in my part of the world are almost all now being built with foam insulated concrete forms, and the numbers for those are terrible. 33 tons of emissions associated with making a wall that way. So what this started to point out to me, and there's a bunch of different areas in the building, is that there are some choices that are really, really, really not good in terms of emissions and the effect that a building has on climate change. And then there's a whole bunch that are not only not bad, but are actually positive for the climate, that actually draw CO2 out of the atmosphere, which is something that most climate scientists say we need to not only cut our emissions, we need to get a bunch of the CO2 that's in the atmosphere out of the atmosphere. And so these materials really kind of point the way to being able to make complete building assemblies that on the whole are drawing down. So the last few slides were sort of showing you different elements of the buildings, but what I did was I sort of took the worst ones, and that makes up the red bar on this graph. I took the blue bar is sort of, I just chose materials that are extremely common for these types of buildings in my part of the world. So that would include sort of a concrete foundation with some foam insulation, wood-framed walls with fiberglass insulation on the inside, and a foam cladding on the outside, asphalt shingle roofs, fiberglass in the attic, vinyl windows. I kind of did a survey of what is the absolute norm for my part of the world, and I got that blue bar. The yellow one, what I did was I chose all the lowest emitting or carbon storing materials that I could find that are commonly available in the market right now. So that would include things like cellulose insulation, wood fiberboard sheathing, various wood products in the building. That building had a metal roof, but things that are really accessible to pretty much any builder right now. And it was interesting that those off-the-shelf choices turned that building into being just below the line. So it turned it from being an emitter into a small-scale store. And then the green bar was I just chose all the best materials, and most of these aren't things that are in common use. So that would include things like straw bale walls and compressed straw board panels on the inside as dividing walls and things like that. But all things that people do use that code approved buildings have been made out of, and in some jurisdictions, especially in the European jurisdictions, are things that you can go buy off the shelf. So they're not things that are dreamy and things that we could never do. They're just things we've kind of, to this point, chosen not to do when other people have. And the two different sets of graphs are from the, yeah?
I saw EPS and XPS insulation. How about polyiso? Are those?
I didn't, polyiso I didn't put that in my list. It's not very widely used where I am, although I know it is in lots of places, but it's the best of all the foams when I look at the numbers for it, which makes it the best of the worst category of materials. So all the foams are worse than every other insulation, but polyiso would be the best of the foams and puts it quite close to things like mineral wool and fiberglass that are at the high end of the not so good range. So, yeah. So the two different sets of graphs. The one on the left is the code compliant version, and the sets on the right are if I made it net zero ready according to the Canadian codes. So what you can see is that on the red and the blue bars, there was an uptick in the carbon footprint because basically we added more insulation materials, and those insulation materials had emissions associated with them. And then you see a slight, also, I guess not an uptick, maybe it's a downtick on the yellow and green bars, because again, we added more insulation, but the insulation was now carbon storing instead of emitting. And so that right away sort of opens up this really interesting pathway where, clearly if we're going to build with emitting materials, we have to think carefully about whether we should be using more of them. Like, is the uptick in embodied carbon emissions does it actually get sort of paid back in a reasonable time window by reducing operating emissions? And we'll look at some of those numbers in a minute. But what this makes really clear right away is that you can't go wrong for the climate insulating more if your materials are carbon storing materials. So, it's kind of a double win scenario. If you can put more insulation in that stores more carbon and it makes the building emit less carbon over time, that's a good scenario. So that's results for, two small buildings. But what I want to do is just get a quick snapshot of how many of those types of buildings get built. And here I used US numbers. I thought you would be more interested in these. So in 2017, about 240 million square meters of this style of building got built in the US. That was a fairly average year if I looked at the last sort of 10 years. And so that means if we build the buildings as a mix of the red and the blue bars, so the worst and the typical, they have about 345 kilograms of CO2 per square meter associated with them. If we multiply it by that number of square meters of those kinds of buildings, it's 83 million tons of CO2, which is the equivalent of about 23 coal plants worth of emissions. So, on the whole, like every small building, it's not that big a deal, but when we think about them collectively, it is a pretty big deal. And if we were to build all of those same buildings, that same square footage, in the sort of best case scenario way, with lots of carbon storage in them, we would not only not emit that 23 coal plants worth of emissions, we'd store the equivalent of 10 coal plants worth of emissions in those buildings. So in 1 year of just residential small scale building, we could have the effect of basically taking 33 coal plants offline, it's big. In Ontario, we had 6, and it was the single biggest emissions reduction in North America ever. And so that was a one-time, reduction. This industry has the possibility of being able to reduce on this scale annually. So now we'll sort of look at the operational side, and there's a lot to kind of unpack in these graphs, but for explanation, the two on the left are the code compliant and the more energy efficient version of the highest emitting building. The two in the middle are what had been the sort of blue typical version. The next two over are the best materials from the available material palette, and on the right are the best ones. So the bottom bars of the graphs are the embodied carbon. So that's the same figures we just looked at. So the 207 tons and the 235 tons, that's for making that high embodied carbon building. The yellow parts on top are their operational emissions in the window between 2020 and 2050. So I'm only sort of looking at a 30-year window, and kind of chose that because that seems to be what most of the climate scientists tell us. We got to do something in this window, or all bets are kind of off. So I was curious, what would the impact be in those 30 years? So you can see that the yellow numbers are kind of the same for all the buildings, right? It didn't matter how we built them. If it was to code, there's 270 tons of emissions over those 30 years. And if they had improved efficiency, there's 213 tons over those same years. And that's the same the whole way across. So it doesn't matter how you build it, if it's X level of energy efficiency. And this is using natural gas as the heating fuel. So you can see really interesting things happen where you do end up having some savings overall over the 30 years from making this building more energy efficient, but it's pretty small. It doesn't add up to much. So the overall emissions. There's 477 tons to 448. So it's a minor improvement, but it's not massive. But what's interesting is that, for example, this one here, I can build that building and run it on natural gas for 30 years, and it'll have a smaller carbon footprint than making either of those two buildings on the left.
In the very, very first slide,
Yep.
You had a increase in operational emissions quite substantial.
Yeah.
Especially past the 30-year window. What do you attribute that huge
Well,
growth to?
If you take that 270,000 number and divide it by 30, that's the annual emissions. So in that first graph, those are being added up over 100 years. So
Okay.
every year you're accumulating the same amount, so it sort of has a linear slope upwards. Yeah. On the far right, those buildings, if you build them with all carbon storing materials, actually bring the overall level of emissions by 2030 down to, again, sort of like lower than even building the buildings on the left, so that it's possible to make a building out of those materials and run it on natural gas and have a smaller overall carbon footprint over 30 years than the high emitting building had just being constructed in the first place. So those are pretty encouraging figures. But then I also modeled them if we used electric powered heat pumps using the Ontario electrical grid. And the Ontario electrical grid is a pretty clean one. We have a lot of hydropower, and we also have a lot of nuclear power, and there's a whole debate to be had about how clean is nuclear power really, but in terms of like the actual emissions that are coming from running that nuclear plant, they're very low. And so look what happens to those yellow bars. They disappear almost completely because the fuel that we're running the building on doesn't emit. So right away, this says to me, beyond even what materials we choose to use, the fuel source that we're using is the point of biggest leverage. If you can get these yellow bars down to the size of these ones by cleaning up your fuel source, that's worth doing. And once you have a clean fuel source, what happens is that in our climate anyway, adding more insulation to that building isn't really having any positive effect on the climate. You can see on any of the ones on the right of the pairs, the one where we put more emissions into the building to add more insulation, they just carry that negative quality with them through their whole life because the operational emissions become so low. And on the right side of the chart now we're talking about buildings where the carbon storage of the building is meaningful and lasts, in the case of the buildings on the right, almost 2 centuries. So if our operational emissions can be made small like this, which they can, that's just cleaning up our electricity grids, then these buildings become sites of really sort of valuable and meaningful carbon storage, like the kind that you can count on scale to make a big difference.
What sort of heat pump efficiencies did you use for that?
So these are air source heat pumps with a COP of like between 2.5 to 3. And the person who did the energy modeling for me did like hourly modeling. So when it was really, really cold, the heat pump was probably running closer to 1. And when it was warmer, it was more like 3. So they're sort of, the figures are averaged out to, not averaged out, they're specific to the actual time of use of those. Yeah. And again, I think it's easy to just, think of, oh, heat pumps, they're the quick fix. What this graph doesn't show is that, the refrigerant in most of those heat pumps is a really potent greenhouse gas. And if somebody messes up the installation and lets all that refrigerant into the air, you're now probably looking at this again because it doesn't, this is one example of using clean energy. It may be that it's actually better to just use electric resistance heating, in which case we'd be using more electricity, but if that electricity is really clean, then there's not a lot of emissions associated with it. So there's lots that we could talk about and think about, but just this really just points to the fact that cleaning up the grid and then using cleaner power for our buildings makes a huge difference and makes making the carbon storing buildings really meaningful climate action. So then I sort of graphed these things out so you could sort of see. So the very worst case scenario is a high carbon materials building using natural gas. So you can see you start with the yellow bar, that's your embodied. Over the 30 years, the red bars keep climbing, and so that building ends up being just shy of 100 tons. And then my best case scenario was the building starts as a storage medium. The slope up of the operational emissions is really small because of the heat pump and the clean grid, and it's still a site of net carbon storage by 2050 and remains so for a long time. So, when you kind of see those two examples side by side, it's a pretty, there's a stark difference between them, and sort of points to, what kind of impact we could have on the built environment by thinking about it this way. So then these, magic carbon storing materials that make a building into a carbon storage device instead of an emitter, there's nothing particularly magical about them. Most of them are either agricultural residues or forestry residues. I didn't actually count the carbon storage value of timber in any of my diagrams, so or in any of my case studies. The case for whether wood is a meaningful place for carbon storage or not is really complicated, and depending on who you talk to, you get very different answers. But the key issues around counting the carbon in wood have to do with, when you take a tree down, just like all these other plants, it's made of about 50% carbon, so there is carbon stored in it. But by the time the tree becomes a piece of wood in your building, about half of that tree didn't make it into a building or any other product. And so if the other half only got burned, or if it only rotted, or if it wasn't sort of handled appropriately, then 50% of the carbon is now in the atmosphere and 50% is in your building. That means you didn't actually store anything in your building. It's sort of like a net neutral. And then if the tree that got cut down isn't replaced, then it would have gone on storing carbon, but now you cut it down and it didn't. If new trees are planted, it takes them a long time before they're big enough to be storing the amount of carbon that was going into the big tree. If you cut down a lot of trees and expose the forest floor, a whole bunch of carbon comes out of the soil. And so there are the calculation for figuring out whether wood has meaningful carbon storage gets really complicated. The building industry basically has taken the fairly simplistic approach that if it's FSC certified wood, then you can assume that the carbon stored is meaningful, and if it's not, you don't. I'm not quite sure if that holds up, but it does point to the fact that how we harvest wood, how we treat wood, what we do in forests matters a lot. And if we do it really well, then wood products could be a really meaningful, bunch of carbon storage in buildings. But if we do it poorly, we're just going to repeat old mistakes, which is we're going to just start hacking down more forests because if people are going, yeah, wood is great, it stores carbon, and we're going to, demolish forests and no longer have these really important soil carbon and forest carbon sinks. So it's a tricky one, and so I didn't want to sort of weight the study towards wood, but it's not that wood is bad. It's just you have to be very thoughtful about it and know where it's coming from to count it. But all of these other things are things that are either from waste stream fibers that already exist, or they're agricultural residues that are things that we're currently growing. And just to give you some sense of the scale, just in grain straw, so just in basically wheat, oats, barley, rye, things like that, on a global scale, we grow about 2 billion tons of these a year. So not the grain that we eat off them, but there's 2 billion tons of straw left over from doing that. And there's enough carbon in all of that straw that has actually soaked up all the transportation emissions globally, but then we just either burn it in the field or let it rot or plow it under, and that carbon ends up sort of back in the atmosphere again. So what's interesting about all of these agricultural residues, and then things like cellulose insulation, which is recycled newsprint, so used to be a tree, then got made into paper, and then got made into insulation, or wood fiber board panels, which they're taking sawdust from mills and compressing that into insulation. So all of these things exist already in really, really large quantities. So one of the big concerns about, trying to steer people towards doing things that are better for the climate is, are there unintended consequences? So what we don't want is for, people to go, oh, well, then we should be building with straw, and we should cut down all the forests and grow more grain so that we will have this straw to make houses out of. But what's interesting is that we have enough of all of these materials already. Like, we don't have to reinvent anything. We don't have to start new industries. We don't have to plant new things. We can just take what we're already growing for food and use the byproducts in smart ways, like by putting them in buildings. There's also really interesting stuff going on around using more mineral-based materials, or carbon that was plants and has been pyrolyzed so that the carbon is now not in plant form. Cement replacements like rammed earth and cement, Portland cement replacements like palm kernel ash and rice hull ash, things like that, where plant material becomes in a different form, that carbon gets used in buildings. That's more, there's not a whole lot of this going on right now, but it is a really interesting set of opportunities. And then really interesting things, things like mycofoam, which is growing mycelium insulation. We did this on a project a couple years ago, and it was great to, basically to be able to grow materials. So even getting away from that whole paradigm of, you go out into nature, and whether you're harvesting rocks or harvesting plants, you're still sort of causing a whole bunch of ecosystem impacts. If you can sort of get these things to grow, independently of nature, then that's interesting. Biomason, I think they're here in North Carolina. It seems to me, I've been talking to them. They're growing bricks, so they have they've developed a microbe, and they put it into sand, and they feed it, and it excretes calcium carbonate and sticks all the sand together, and you end up with a brick that was grown rather than relying on burning rock to make concrete. And then there's quite a few companies now working on taking CO2 out of exhaust flues, especially from cement production plants, and recarbonizing that into aggregate. So turning that gaseous CO2 into rock. So Carbonate and Blue Planet both have pretty good sized demonstration facilities going where they're doing that. So this sort of opens up another whole set of possibilities for carbon storing in buildings. And then this is just, my own practice. Obviously, I'm somewhat obsessed with, the carbon in building materials and this whole notion of embodied carbon, but my own practice comes from being really concerned about all kinds of other things like ecosystem impacts and human health and, a whole range of things about buildings that I'm really keen on. And I know you can't sort of read all the numbers on there, but this is the sort of output charts from two of the models for my study. And what I wanted to point out is the one on the left, that was the high emitting building. Everything, all the materials that are in red contain red list chemicals, so things that are known to be bad for humans and the planet. And the purple bars are materials where the material itself is, we're either running out of it or the harvesting of it causes major environmental problems. And the output on the right is my best case scenario building. And what I love about approaching buildings from the idea of embodied carbon is that I get all the outcomes that I want in all the other categories that I care about by thinking really carefully about material selection from the embodied carbon point of view. I end up doing the right thing for human health, planet health, ecosystem health, all of those other impact categories. The materials that are better for the climate end up being better for us in every other way too. And so, my whole career has been definitely over on the margins of the building industry. I'm working with things like straw bale and clay plasters and floors and hempcrete and materials that are definitely not mainstream. But I think they're not mainstream not because we can't make them mainstream. Like, there's no rocket science involved in putting straw into a building. There's no rocket science involved in putting hemp into buildings. Like, all of these things are actually extremely easy to do. There are people who are already doing them at a reasonable scale. The manufacturing facilities have been developed. It's a pretty small step, and that, collectively, as a species, if we can do some of the things we've done, like building a large hadron collider, we can probably figure out how to bundle straw up into buildings even better than we're doing it now, which is pretty rough and ready. But precast hempcrete blocks, there's a company that just is about 3 years old up in Canada now making those. We've done a lot of work on prefabbing straw bale wall panels in our company, and there are a couple of European companies that do it at pretty decent scale. Stramit Strawboard is a compressed strawboard wall panel. It gets used a lot in Europe, but they have major production facilities there. So these are all things that, with even just a small bit of interest and enthusiasm, we could definitely be turning these materials into mainstream construction products. There's not really much holding us back from doing that. One of the things that I think about a lot in my own country and here too is that right now there's seems like politically a pretty big divergence between sort of rural America and farming America and people who are keen to do something about the climate. I think that the rural parts of North America and those economies, if we could show them that there's benefit to be had, that we actually want to pay them for more stuff that they're already growing, and that there are opportunities to do small-scale manufacturing on the farm or in those small towns, like that's that's a great way to win people over to the the climate saving team, is to show them that it's also a major economic opportunity, and I think it really is. A lot of these types of materials, they don't benefit from the same production model that the building materials world has right now, which is, there's one styrofoam factory and all the raw materials go there and all the finished product goes out across North America. These kind of things benefit from, you've got a good wheat growing region, make the straw panels there and send them out regionally. And if, in Louisiana you've got rice, not wheat, then you do a factory there that's doing that. And all of these things have really great sort of potential for small scale regional production.
Are the straw boards, are they sort of a substitute for XPS and that sort of thing? Is that the idea?
These particular ones, no. This company makes them as their interior wall dividers. So they're actually like rigid panels, 2 1/4 inches thick, that have a C channel at the top and the bottom, and they kind of get used as sort of movable interior wall dividers. But yeah, things like the wood fiber board is a replacement for foam on the exterior of buildings. We've got one small production facility in Canada, but there's really cool products that come out of Europe that we can and should be making here out of forestry waste stream. So if you are sort of interested in this, there's a group called the Carbon Leadership Forum, and they have this Carbon Smart Building Initiative that they're looking for sort of individuals and organizations to sign on to, and their mandate is exactly what I've been talking about, to sort of transform the built environment into a carbon sink instead of a carbon source of emissions, and to sort of do so at a pretty large scale. So if you're sort of interested in getting involved and learning more about it, there's great resources on their website. And just to sort of give you an example that these aren't made up figures, or that these are sort of dream buildings that we might be able to do someday but aren't doing now. This is from our own sort of portfolio at Endeavour. I have a feeling I've only calculated this for 3 of our buildings that I'll show you, but I think it goes right across everything we've done. But so this was a residential infill building on the urban center, and so this particular building has about 39 tons of net carbon storage. And I like to show these pictures because, having net carbon storage doesn't mean that we don't use any materials that have emissions. There's still some concrete involved in the foundation of this building. It's got glass in its windows. There's no non-emitting glass yet. It's got a steel roof. It's got a whole bunch of things, nails and screws and stuff that have emissions associated with them, but there's enough plant-based materials that we actually offset those and still have net storage. And then, obviously still concerned with things like making the buildings energy efficient, thinking about renewable energy as part of that clean generation. So, the building has PV on the roof and solar hot water and things like that. And then also, goals around having no toxic or even questionable chemicals in the building, really cutting down on construction waste. All of those goals are there. And we get 40 tons-ish of storage. This is a small office building that we built for a teachers union local, and it's a great carbon store. It's 71 tons in a 2,400 square foot building, so that's way higher than anything that was on any of my graphs. And again, using renewable energy, still using emitting materials. There's steel siding, steel roofing. The PV panels themselves have a carbon footprint. We sort of, calculate all of that in, but you can still get really meaningful amounts of carbon storage. And then this one is a little house that we did with a local university. They designed it. They designed a stackable row house development, and this little building is sort of like one piece of that. So right now it exists as an individual home, but the idea is it would be one part of a stackable row house. And so this was all done prefabricated and modular, so that we were able to build it. We actually built it and assembled it in our city, took it down, put it up at a design show that the university was involved in Toronto, and then took it down and put it up on a client's site. So that's another thing, sort of, looking at, if you take the sort of notion that, okay, a building can store carbon seriously, then you sort of extract that and you think, okay, well, what happens at the end of this building's useful life? Does all that carbon just get released? Maybe it gets turned into biochar, but this building was us thinking, well, if you make buildings in a very modular way where they're easy to take apart and dismantle, if this person doesn't want this home or a bigger development is coming along, if you can easily take that building apart and rebuild it somewhere or put the parts of it into another building, then that carbon stays, out of circulation for even longer. So I have a particular sort of fascination with that kind of modular approach. I think that the building industry this is a really interesting opportunity, because not very many other industries that are major emitters on the planet have the opportunity to transform themselves from emitters into carbon storers and still being able to do what they do at the scale they do it at. Like, if you're an oil producer, you're pretty much looking at having to get out of oil production, at some point in history. We're not asking the building industry to stop making buildings. We're just asking them to make them out of smarter, better materials. But in fact, growth in the built environment, if we're doing it with carbon storing materials, is actually potentially really beneficial to climate change rather than detrimental. And so, it's the only industry that we can sort of make that ask of, like, don't stop doing what you're doing, just do what you're doing in a better way, and the same level of employment and opportunity and sort of like economic production is still there. So I think it's a really interesting opportunity for this whole sector to be thinking about seriously. And yeah, if you want to dive into this in any more depth, there's good resources on all of these websites. And I'm glad to make the slides available to you through the Green Built Alliance, if that's a possibility. And can do that. And I'm also happy to chat about things, take questions, talk a bit with people if you have things you want to ask. Yeah.
What's the cost differential between the commonly used materials that have a high carbon emission versus the ones that you're speaking about with the plant-based materials?
Right. Pretty small. Like right now, I've got the cost figures that we were able to do these things for. So a prefab custom house for $250 a square foot, an office building for $210, this house for $170. So it's not a huge difference. The biggest difference right now is that not that the materials cost more, but that a building company has to invest more time in finding them, because you're not just going to Home Depot, you're finding a farm and talking to that farmer, and so it's more the things that make it more difficult aren't money, it's time and availability, code issues, things like that, all of which you can overcome, and all of which the building industry can overcome very quickly with concerted effort. But right now, the early adopters, they're not paying more for the materials, but they're paying more in their time and research and code applications and things like that to make it happen.
A question on your books. I'm not planted here to say that, but I was curious, what's the difference between the 2014 Better Buildings?
Making Better Buildings, yeah.
And the newer one, which I don't remember.
Yeah, so Making Better Buildings is where I stumbled into all this data. So it's really a materials book. Like it's got every material that I could track down any information on, both sort of conventional and alternative materials, with things like the carbon footprint, costing, how codes work, where and when you would want to use them. And the other one, the essential home design, is more about that. Is more how to think about what you want to build and how you might want to build it, but it's not as deep a dive into a whole range of materials.
Do you have an opinion about an alternative to polyiso for exterior roof insulation?
Well, I mean, there are a bunch of companies that do make wood fiberboard versions of that. And the North American made ones aren't the greatest, but they're there. But the Europeans have some really good ones. They're like wax impregnated wood fiberboard, so they do well if the roof does leak. They don't just melt and disappear on you.
Okay.
But I think there's also, the way I'd like to think about this is, if polyiso is the only option for the roof, then what else are you doing elsewhere in the building that might store and offset that polyiso? Like, I don't think thinking about this necessarily means like, don't ever use concrete, don't ever use, it's like, think about if you have to use emitting materials, what storing materials are you using to make sure that...
I can justify polyiso in this situation.
Yeah. Yeah, I mean, this building here, it's got a bunch of emitting materials in it. It's just, in the places where it was practical and made sense, we used storing materials, and that's a strategy. Like you actually plan that out and you think, okay, if I'm going to take an emissions hit here, I'm going to make up for it somewhere else, and that could be on buying a clean energy contract for the building too. It doesn't necessarily have to be materials based, but I think the thing is, up till now, it just hasn't been on anybody's radar to think about that at all. Like, it's just been what material seems to be the quickest, easiest, fastest for that solution, and its carbon footprint hasn't been part of that equation. And I'm just trying to make it so that people sort of think about it and not to prescribe only using one or the other, or saying you shouldn't use certain things, but that there's a balance and you can sort of figure out how to strike that balance so that it works out well.
That's really helpful. I was eager to use the wood fiber insulation, but I was intimidated by sourcing it.
Right. Yeah. Yeah, and that's a real.
I want to use that, but man, the internet is so deep.
Yeah. Yeah. The three European companies, Gutex, Styco, and Habitex.
Okay.
They're all really great. I don't know if there are distributors in this part of the world, but we've used lots of all of those products, and they're pretty amazing.
Okay.
I wish they were being made here, because if they were being made here, they would be cheaper than everything else. As it is, they're like the same or a little bit more because somebody's bringing them in small batches from Europe and sub-distributing them and stuff. But, there's a factory starting up in Vermont that's hopefully going to be producing that kind of stuff in the next year or two. Hopefully we'll see more of that. It seems weird that the Germans, who don't actually have any trees of their own anymore, make the best wood waste building materials, and they actually have to bring in the wood waste from other places. But we definitely have the raw material here, so I'd love to see that happen more.
Thank you.
Can you speak to fly ash in concrete? Like, if it's toxic to do so, if it's inert, if we use it in concrete, what impact does it really have if I tend to order 20% fly ash for footers and things like that?
Yeah. I mean, it's an interesting one. That fly ash still has emissions associated with it.
Sure.
But in the emission shell game, what gets said is that, well, the coal is going to be burned anyway, so whatever is left over from that, this fly ash, let's not associate any of the coal burning emissions with it. We'll say that it's got no emissions, and so if we can replace a bunch of Portland cement that does have a bunch of emissions, we've done something. And there's something to that. Like, if you could offset the amount of Portland that has to be made that's worthwhile. I mean, as to its toxicity, everything I've read is that once it's bound up, it's stable. But I was just in Seattle and I was walking with a friend and we were watching them take down this huge overhead highway downtown and like cutting all this concrete, and there's like dust everywhere and they're spraying with water and the water's running into the harbor. And it's like, well, if that was fly ash concrete, all the stuff that is bound up and wasn't toxic is now, flying around or ending up in the water. So it's like it's good in the window of time where we're doing what we're doing with it, but it all those heavy metals and stuff, they will come out at some point. There are other like up in my part of the world, we don't have fly ash because there's no more coal burning. So steel slag is a cement reducer, has the same properties, and same idea. Like you're heating up all this ore to get the iron out of it, but you fired it in the same way that you would have fired the limestone to make Portland, so it's reactive in the same way. So there's, those things make some difference for sure. A better difference would be palm kernel ash or rice hull ash, where you're taking an ag resource that is stable, that is not toxic when it comes out, and not having to burn coal in any form to get it. So, but also hard to find, right? You're not going to call up any patching plant and ask for 20% rice hull ash concrete. But we could, like that's the whole idea of this, is we need to start pushing for those things. They exist. The science is there to improve it, and the stocks of them are there. It just has to be a reason for people to want it. And I think lowering that carbon footprint is hopefully going to be a reason that'll start to happen.
One other question: when you cite XPS and its carbon impact, is that a carbon equivalent based on the blowing agents used to produce the XPS? Okay.
Yeah, so all those figures are CO2e, which is equivalent. So yeah, it is looking at all the emissions associated and putting them in terms of carbon, so it's not, And I mean, interestingly enough, like that number is an average of the two main XPS manufacturers in North America. So we've got Dow and Owens Corning. Dow's is way cleaner than Owens Corning's. Like what I'm showing is an average, but if you actually dive into like product by product, sometimes, and the European XPS is way better than anything being made in North America, and I'm not sure why that is, but so that's why for this I was sort of choosing averages, but the whole point of those environmental product declarations is that you can go as a specifier and choose the one that has the lower global warming potential and make that like an intentional product selection criteria.
Do you know which product our board uses? If it's Dow or?
I don't, no.
I find it a challenge to calculate the embedded carbon in a product. And you mentioned wood as being, who knows what it's worth. We don't use concrete, we use wood foundations with the assumption that we're sequestering carbon.
Well, at the very least, you're not emitting much carbon. So even if you look at wood just from the emissions side, which is what I've calculated here, it's like lower by a order of magnitude than concrete. So it's not the wrong thing to do. But I don't know that unless you know that you've got really sustainably harvested wood, that you can count it as storing that carbon.
Okay. Well, I'm a big advocate of putting a price on carbon, because then all these issues, the difference between Dow and Corning would evaporate, because they would both be competing to get the lowest price, and all the builders would motivate using
it seems like a pretty easy solution. It's kind of shocking that there's been so much resistance to it, but that would make all the difference for everything I'm talking about here. If suddenly a builder or a building materials company was being rewarded for storing and having to pay for emitting, that would be a big game changer.
And for example, the fly ash we use in rice hulls does that reduce the amount of Portland cement in
Yeah.
the block?
It can. I can get a 50% slag mix where I am without any additional engineering, so I can offset half the Portland content that way. So yeah, it can make a big
That's
difference.
the total content of Portland cement.
Yeah, yeah.
Okay.
Oops, yeah.
So, standardization in natural build, I love the fact that a lot of these houses built conventional because, not that I don't like natural building in that style, but, you know, construction time is money and labor is the biggest cost. And there's a lot of natural building companies in the area that do mainly workshops, but it's a hard business model because of the lack of standardization of materials. So like the hemp fiber board and different natural materials put into conventional you know, shapes and sizes. Are you guys seeing more of that in Canada?
Maybe a little bit, like the precast hempcrete blocks is a really interesting one. And that one is interesting because they've built the structure into the block, so it's not you frame and then you put this insulation in, so it's in one step you're getting structured insulation. Our own sort of like work with prefab straw bale panels, it's all been sort of a reaction to that. It's like, okay, you know, for this to work at any sort of scale, you do have to make it fit, you know, a sort of time equals money standardization. And I think, you know, to the degree that people at my scale are able to do that, we've done a good job of doing that. But, you know, I think, okay, so the people at Dow figure out how to get oil out of the ground, do all this stuff, and like blow bubbles into oil. It's way easier to figure out how to make a straw bale into a nice square package. Like that shouldn't be you know, a limiting factor. I think it's pretty easy to do, and I think we'll start to see more of that. You know, the prefab stuff, the prefab straw bale stuff in Europe is really interesting. The precast hempcrete wall systems that are there, the wood fiberboard stuff, like all, you know, it's not from a manufacturing point of view not hard to do. So, and I think that's where like a carbon price or, you know, some sort of incentive to be interested in doing it in the first place from an economic point of view is, you know, that would help a lot.
On the rice, I was surprised to learn that rice cultivation is like an incredibly large source of carbon dioxide.
Yeah.
So basically, people are gonna, it's like a fly ash. People are still going to grow rice, so we just have to do the best we can using the hulls to help offset that.
Yeah, and you know, in all the card, like in my calculations, all of the growing emissions are factored into that.
Right.
And the ISOs come up with all sorts of things. Like, so if you're growing rice and rice is the main product, you attribute 70-something% of all the emissions and the impacts to the rice and the rest to the byproduct. So like all of these calculations for whether it's wheat straw or rice hulls or anything, it's sort of taking the slice of the emissions that those materials are responsible for and working that into the calculation. So it's not turning a blind eye to the fact that the way we grow these things right now are responsible for a lot of emissions. But if it's responsible for all those emissions, we might as well harvest that carbon byproduct and help offset that.
And we're not going to cut down forests just to grow rice so we can harvest the 30%.
That's right, yeah.
But do you know why rice is so impactful?
I don't actually know. It's probably, the carbon footprint is likely because I know this from looking into like hydropower, which people sort of say has no carbon emissions, but it actually has fairly big ones where water levels vary in a dam. So when the water goes up and it covers plant material, that plant material sort of rots and becomes methane.
Exactly.
So I think probably the flooding of rice paddies I'm guessing,
Oh, yeah.
has a similar effect, because you are sort of flooding those areas for a period of time and then letting them dry out again. So,
Plus the concrete embodied in the dam must be significant.
yeah,
size
well, that's
of
where the whole thing about nuclear energy being carbon neutral.
Yeah.
It's like, well, if you ignore all the concrete that went into making it, then maybe. But I think it would be a lot like this. Like you would see, there's actually this huge burst of emissions to make the plant in the first place that would offset that sort of clean energy for a fairly long period of time. Okay, well, thank you all so much for being interested and great questions. And I'm around, so if you want to chat afterwards, I'd be happy to do so. And thanks to Greenville Alliance and the college for hosting and putting all of this together. It was a lot of effort on your behalf, so thanks for that.
And come back at 1 for the next workshop, which is designing your own sustainable power.